Wonderful. Hello, everyone. This is Ebrahim Begheri. I'm a professor at the University of Toronto, and I'm hosting Jingtao Zhan today for the SIGIR VF talks. This is a part of the SIGIR VF Best Paper Awards series. I'm very happy to introduce Jingtao to you, who is a Ph.D. candidate in the Department of Computer Science at Tsinghua University. His research primarily focuses on natural language processing and information retrieval, with particular interest in dense retrieval techniques, model interpretability, and the analysis of large model logs. He has published numerous high-quality papers at top international conferences, such as SIGIR, ACL, WSDM, and CIKM. Two of his papers have been awarded the Best Paper Award, one as the first author and the other as co-first author at WSDM 2022 and SIGIR 2024, respectively. He's presenting today the paper that received the joint Best Paper Award at SIGIR 2024, titled Scaling Laws for Dense Retrieval. Thank you so much, Jingtao, for joining us again and presenting your work. The virtual floor is all yours.
Thank you very much for this very nice introduction. And today I'm going to talk about the SIGIR paper and my recent study. I think this would be a very interesting talk. The title is Scaling Laws for LLM, Ranking, and Intelligence. So first, I think maybe we are familiar with the scaling laws for large language models. This is probably the reason why so many companies are trying to scale up the model size and why NVIDIA has the market value of NVIDIA has reached so high. So for scaling laws for large language models, we use the objective as the perplexity, and that is a cross entropy loss for predicting the next token. And researchers have empirically found that if we draw a log-log plot, the x-axis are the model size or the data size or the cost of training, and the y-axis is our objective, the perplexity, or we call the cross entropy loss. We can find the data points all fall along a straight line. This means that the relationship is approximately a power law. And in this way, we can know exactly what will the objective be when we increase the model size or the data size. And this is what OpenAI empirically found in 2020, and this has been very popular for existing large language model companies for the reason to scale up their model size. And we try to find whether this also holds for ranking. And therefore, in 2024, our paper tries to empirically find out the relationship between the ranking performance and the neural ranking model size. And we use a model that we call a dense retrieval model. The dense retrieval model, or we call it a two-tower model, has two encoders. One encoder is to encode the documents to embeddings, and the other encoder is to encode the queries to embeddings. And we use embedding similarity as a ranking score. And therefore, we can rank the documents from the highest to lowest so that we can present the top documents to the users. And when we try to investigate the scaling law, we still use the perplexity as our objective. This is also a similar cross entropy loss, like what OpenAI does to investigate the scaling laws for large language models. And we try to answer the questions like how to evaluate the model, how does the scaling affect model performance, and how should we scale in practical scenarios, things like that. And we try to find out whether the model size or the data size has a similar power law effect for ranking performance. And this is what we find out. We try to find, this slide shows the model scaling law. We conduct experiments on MS Marco, T2 ranking. The two datasets are web search datasets for English and Chinese respectively. And the model size ranges from 0.5 million to 100 million. And we use data sets as 500,000. And we can find out the data points exactly fall along straight line as what OpenAI find out. The x-axis is model size and the y-axis is contrastive loss. And we can, the two axes are all on a log scale. We can find out the left side is an English dataset and the right side is a Chinese dataset. We can find out the data points for all fall along a straight line, showing that this actually is a power law relationship. And this is the model scaling law, so we can have a this mathematical formulation to show the relationship between the model size and the cross entropy loss. The N is the model size and L is the cross entropy loss. We also can find out a similar data scaling law. The x-axis is data size, and the y-axis is cross entropy loss. We can find out the data points all fall along straight line, showing that their relationship is a power law relationship. So that if we increase the data size, we can know what the cross entropy loss will be. They will fall along this straight line. So the D is the data size and the L is the cross entropy loss, so that we know this is exactly what the data size, the effect of data size on the cross entropy loss. And now we can also fit a joint scaling law, showing that this is we can know exactly how different combinations of model size and data size, we can know their what's the cross entropy loss will be. We will have this formulation and the fitting result is good. And this also echoes what OpenAI find out. Now we can have a quick summary about previous scaling law studies. We try to evaluate the performance as a perplexity. This is also what we call cross entropy loss. And we can empirically find out the effects of model size, data size, and the combinations. There we have a good formulations and they fit the data very well. However, for both OpenAI studies and our prior studies, the results do not have a very good physical meaning. I mean, the perplexity actually is quite confusing. We don't know what perplexity actually means. For example, we don't know if we decreases the perplexity for a little bit, what does it mean for actual applications, or what does it mean for the model performance when users interact with this model. So actually, although we have a good math formulation that shows the effects of model size and data size, but we do not know how large should the model be if we want to reach AGI. And this is the most important problem, I think, for scaling law studies, because this mainly stem from the fact that the objective or the performance we use, the perplexity, is quite confusing. We don't know how small should the perplexity be so that we can reach AGI. So we have a recent study. We try to quantify intelligence in a very intuitive way, so that we can know exactly how small, how good we should reach so that we can get to AGI. So what is intelligence? This is a very broad question, as Turing said in his famous imitation game paper. We cannot actually define intelligence because otherwise we need to do a survey for everyone and actually collect their information, but this is not what science does. Instead, we should propose another question, an ambiguous one, so that we can know, so that it is related to this question, but it is unambiguous, and we can actually answer it. And we propose, how does intelligence emerge? We want to know for how we can propose a test so that we can know exactly when AGI actually comes, and we can clearly define different levels of intelligence. And I think the quite obvious answer is that a natural way to define or to test intelligence is natural selection, because natural selection is nature's way to filter out the unintelligent and only to let the intelligent to survive. We can imagine natural selection as a survival game. Actually, we have a species with n individuals, and we let them answer questions one by one. If an individual gives the incorrect answer, he will be vanished. And otherwise, if the individual gives the correct answer, he will pass the game. And if at least one individual passes the game, this species passes the survival game. And this is actually our abstraction for natural selection. As we can see that if the species is a failure count of the species is less than the total number of individuals within the species, this species pass the natural selection. And if the species passes the natural selection, it has a very strong physical meaning. It means that the species acquires the ability to survive in the nature. It can be autonomous to operate in the nature world. And as Charles Darwin said in his Origin of Species paper, but natural selection, as we shall hereafter see, is a power instantly ready for action and is as immeasurably superior to man's feeble efforts as the works of nature to those of art. And this is the reason why we can see so many intelligent species today, not only for humans, but also for dogs, cats. They all pass the test of natural selection, and they are intelligent in terms of survival. Inspired by this survival game, we propose a new test for intelligence. We call it intelligence test. We try to extend the test of natural selection to any task and to any species, so that we can know how good they are in terms of autonomous operation within a task. We use a statistical basis, that is, for any task and for any subject. We model the failure count as a discrete random variable. And for example, we let the subject to try, for example, to prove a math question again and again, and to model how many times should the subject try before he can actually arrive at the correct proof or solution. And this failure count is a discrete random variable. And the smaller the failure count, the high intelligent the subject is considered to be. And we can define intelligence in this way, so that this discrete random variable shows the subject's intelligence. And we can define 3 intelligence levels. For the limited level, the expectation and the variance of the failure count are both infinite. For the capable level, the expectation and the variance, the expectation is finite, but the variance is infinite. For the autonomous level, both expectation and variance are both finite. And it has a physical meaning, means that if a subject reaches autonomous level, it means that it can stably find the correct solutions within a limited step of attempts, so that it actually can find the solution with its own effort, and the effort is affordable because it's finite instead of infinity. So that if a subject reaches autonomous level, it does not require any more external supervision, and it can autonomously operate by itself. So how do we actually, given the failure count and to classify it into the 3 levels, we can use a power law references to classify it. So we can examine the convergence based on the probability dense distribution based on the failure count. So whether the expectation and the variance converges, it depends whether depends on whether the tail drops quickly enough. As the tail drops quickly enough, the expectation and variance will converge. For example, for Gaussian distribution, the expectation and variance are both convergent. So to examine whether they are convergent, we compare the distribution with the power law distribution with exponents -2 and -3. And we draw this log-log plot. The x-axis is the number of failures, and the y-axis is the frequency or the probability. And we use a log scale so that for both power law distributions, they are straight line in this figure. And we can, for any subject, we can draw their actual distribution of failure count in this log-log plot. And if the distribution falls in this region, it means that this subject is at limited level because the decay rate of their tail is lower than the power law distribution with exponents -2. But if the distribution falls in this green region, it means that it's faster than -2, but it's slower than -3, so that it belongs to the capable level. But if the distribution falls along this yellow region, it means that it belongs to the autonomous region. The decay rate is faster than -3. So we can actually determine the intelligence level based on which region the failure count distribution falls in. And we use this method to comprehensively evaluate different tasks, and we can find something very interesting. For example, we can start with our MNIST, this dataset. This dataset is kind of a beginner's task for many AI students. So this task tries to determine what the digit is given an image. For example, we have digits from 0 to 9, and we let the model to classify these images to the actual digit. So we try different methods. For example, we use a linear model. That means that we just input the image and transforms it into a one-dimensional vector, and then we use a linear model for classification. And we also use a MLP model, and we use a CNN model. We evaluate these three models using our method. We can find that the linear model, the blue point shows the performance of the linear model. The blue points all fall within the limited intelligence region, showing that the linear model achieves a limited level of intelligence. On the contrary, for the green region, we have the MLP model. It falls along in this green region, shows that the MLP model actually achieves capable level of intelligence. And for CNN model, the blue points approaches or kind of falls within the autonomous level of region, so that it belongs to the autonomous level. So we can see that even on this very simple task, we can use our method to clearly determine how good is the model, so that we can know for the CNN model, because it has a very good modeling for the images, it actually reaches our autonomous level. So we can proceed with this with this process and try to evaluate more complex tasks. And we evaluate
Sorry, before you go on, can I ask you a quick question?
Yeah, sure.
On the previous, yeah. How do you measure number of failures in this task?
I mean, actually, the failure count is a random discrete variable, so that for different images, we can input the image to the model, and the model will output a distribution for different digits. So that, for example, we can rank these digits from highest to lowest. so that it's a ranking list. As for the model, the ranking list as a strong meaning means that the model thinks the first one is the most probable one, and the second one is a second probable one. So that the failure count means that we can find, for example, the ground truth is ranked, for example, 3. So that failure count means 2. The position of the ground truth -1 is the failure count. Yeah.
Okay, got it. So you consider this a ranking task rather than a classification task?
Yes.
Okay.
And actually for actually different tasks, they can all be transformed into a ranking task. For example, for region, in other regions, for example, clip, we've tried to given a text, we try to find out for image retrieval, it's actually a ranking task. And for language, when we output the distribution on the vocabulary to decide the next token, this can also be seen as a ranking task. So we can all find out the failure count given this ranking list.
Got it. So it's like an MRR measure, basically.
Yeah.
Where in the list does this appear, the correct answer appear?
Yes. Yes.
Yeah. Got it. Perfect. Thank you.
Yeah. And we can draw the distribution on this log plot, and we can find out the intelligence level. And we can see that for region, we use a ImageNet, and the current models are approaching the capable level, but the most data points still lie within the limited level region. And for search, we use many different formulations. For example, we use this shows the MS Markov, and we also try T2 ranking, the Chinese version, and we also construct a synthetic data set. We use a title of Wikipedia page as a query, and we use the body as a document, and try and let the model to find out which body is relevant for a given title. And for all these tasks, the performance all lie within the limited level. And for this is a recommendation, and we use different kinds of methods and real data sets. They all lie within the limited level. And this is for language models. We use, for example, coding, question answering, and we also use something writing just to predict the to predict the next token, and they all fall along this limited level. This means that, for example, we can I think search is the most intuitive one. For example, if we let models if we want to see which one is relevant for us, and if our models are at the limited level, it means that we need to see almost infinite documents until we see an actual relevant one. And if we take recommendation as an example, and if we see one irrelevant item and we are disappointed, it means that we are disappointed endlessly on a recommendation system application. And I think this actually shows that the current models are at a very early stage, and we are far from autonomous operation. And moreover, we can see that these models can be approximated by a power law, because we can see that they kind of behave like a straight line on this log plot, so that we can use a power law to fit the performance. And the power law exponent actually is how good the model is. And with this, we can actually predict when will the decay rate approaches 3, that is autonomous level of intelligence. And we can see that the x-axis is the model size, and the y-axis is the decay rate of this distribution. And they are both on log scale, and we can find that their relationship is actually close to the power law relationship, as we observed for skin loss in previous studies. And we can predict how large the model should be if it want to approach autonomous level of intelligence. That is, if the decay rate will be equal to 3. And for structured tasks, that means coding, law, and math, it will requires 10 to the power of 18. And for some vertical domains, for example, medical, it requires the scale of 10 to the power of 21. And for general domains, if we want the model to comprehend all the information on the internet, it requires the 10 to the power of 26. For such large scale, it is almost impossible to reach given the existing hardware because if we compare it to the total number of neurons of all humans in the world combined, it is 10 to the power of 5 to this number. And if we want to load such large model on H100 GPUs, we do not consider the training cost and the inference cost, and we just want to load them on these GPU cards. It requires the 10 to the power of 7 times the market value of Apple Inc. And if Moore's law continues to hold, it requires 17 years before we can reach such large scale. So that we can see that for current AI systems, if we want to rely on scaling to reach autonomous level of intelligence, it is almost impossible. And actually, we need something else. Scaling laws actually shows that we cannot reach that given the existing hardware, unless we have a major breakthrough in the hardware, for example, quantum computation, things like that. And why does the existing AI technology so hard to reach autonomous level? Why do they exhibit a power law relationship on our failure count distribution? Actually, we have some theoretical analysis. Human task is not that simple. We can see that it shows a critical property. It means that if the environment changes a little bit, it requires a vastly different responses. It does not show something very a continuous function as we assume in deep learning. For example, if we take Fermat's last theorem as an example, the hyperparameter n is the solution to this theorem is very sensitive to the hyperparameter n. For if n is very small, for example 3, people have proved this theorem long ago. But if n is larger, this question becomes much more complex, and the solution is given about several centuries after the theorem was proposed. And for AI, we believe that it currently does not actually understand the mechanism of human task. It actually uses some superficial imitation that tries to solve this human task. We believe it tries to memorize some training data and tries to explore for new questions. And given these assumptions, we can use some theoretical models and simulate the results. And the simulations actually validate, the simulations show similar phenomena as what we observe in our real world experiments. And it actually shows that the human task is very complex. It shows a critical property, and AI is actually trying to use some superficial imitation to try to solve this complex task. And given these two assumptions, it will be stuck at the limited level. And if we want to achieve autonomous level through scaling, it actually requires unimaginable cost. So this is our theoretical analysis, and more details should be found in our paper. And this is a takeaway message. We propose a more intuitive test for intelligence. We do not use something like perplexity, cross-entropy loss because they are confusing. We measure intelligence as a number of failure count, and we propose that, and we evaluate the current AI systems. We find that they are mostly lie within the limited level. It means that the expectation and variance of the failure count are infinite. And we project the future of scaling current AI. If Moore's law continues to hold, it will need 30 to 70 years before we can actually arrive at an autonomous level of intelligence. And given the theoretical analysis, it actually shows that human tasks are very complex. The complexity lies within the search, the recommendation, the vision, and language. All human tasks we are trying to solve in computer science are complex. And this makes the current AI all lie within the limited level for these tasks. And actually, it also means that human tasks are not friendly to AI, especially for deep learning, because we always assume that we are trying to fit a curve that is continuous. But for human tasks, this assumption may not hold, because in human tasks, a small environment change can result in a vastly different response. So this curve is not that continuous and will be very hard for a deep learning model to fit. This is all my presentation. I try to use a very bold topic. So I start with scaling law for large language model, and then I talk about my SIGIR paper, and finally I show my recent study, and I try to find out what the intelligence level is the current system. And I think the projection is kind of it's not that optimistic, and I think maybe people will find it interesting, and I like feedback. So if anyone is interested in this topic, I will be very happy to discuss it with these researchers. Yeah.
Thank you very much, Jingtao. Amazing work, and appreciate your time to present today.